All right, today we're going to talk about similar matrices and how to use them. So before we dive into what a similar matrix is, let's go ahead and illustrate this with a story. So that story is going to be the Frito thief. So just like before, we're going to have different ways of quantifying the number of chips that we have. We can do it in one way. We can do it with just bags, and that will be a basis that looks like this. So these will be bags of chips. And the other way of expressing our quantity of chips is with the party packs. So the party packs might look something like this. These are the same ones as before. And just a reminder of what this represents, this 1, 0, 0 vector is going to represent a single bag of nacho cheese. And this 0, 1, 0 vector is going to be a single bag of Cool Ranch. And this 0, 0, 1 is going to be a single bag of Fritos. And in contrast, over here, these are party packs. So that's a party pack of 50 nacho cheese, another party pack of 25 and 25 of just Doritos, and one of 20 of each. So these right here are just party packs. And so last time we discovered that if you express a quantity of chips in bags, you can transfer that to party packs and vice versa. So for example, if we have something that looks like 200, 150, and 100, we can take that in bags and we can change the basis and express this in terms of party packs. Something that looks like that. That will be 1, 2, and 5 party packs. And of course, how do I do that so quickly? Well, we use, in this case, we're going to use S and S inverse to translate between the two. So S is just the amalgamated matrix. That's just 50, 0, 0, 25, 25, 0, and 20, 20, 20. And S inverse is just that inverse. All right, so you can translate between these two quantities very easily. Okay, but now we have the Frito thief that comes into play. So the Frito thief is going to steal all of our Fritos. So if we have a quantity of chips, say 200, 150, and 100, the Frito thief is going to come in and steal all of our Fritos and only our Fritos. Oops, it's going to steal just the Fritos. And what's may seem a little strange is this act of stealing is the same thing as just zeroing out the Fritos. We're going to zero out all the Fritos that we have. And so this turns out to be the same thing as a linear transformation that looks something like this. So if we multiply 200, 150, and 100 by this matrix, right? The number of Doritos is going to, the number of nacho cheese is going to stay the same. So that's just 200. The number of Cool Ranch is going to stay the same. So that's just 150. But we have a 0 on the diagonal here because the Fritos get zeroed out as to 0. And so this is the matrix. This kind of diagonal matrix is a very special, it's a very nice and easy matrix to handle. And it describes this transformation very naturally. But now we have a problem for the Frito thief. If the Frito thief walks in and sees a bunch of party packs, now the Frito thief is only going to take the Fritos. So if the Frito thief walks in with just party packs, what does the Frito thief have to do? Well, they're only going to steal Fritos. They can't just take certain party packs and walk away. The first thing they're going to have to do is open all of those party packs. And that's done with the change of basis matrix S from before, right? S goes from party packs. The S is going to go from party packs back to the bags. So that's going to be S inverse, or sorry, S. And that's going to translate it into bags. And then the Frito thief is going to come into play and apply the matrix 1, 1, 0 on the diagonal. But now the Frito thief can't just leave the bags out, because then it'll be obvious that they're stolen. We need to put them back in the party packs. So we're going to put them back in the party packs using S inverse. And in this case, this is going to look something like 2, 6, and 0, or 1, 6, and 0. And that's in party packs. So altogether, the entire process of the Frito thief, opening up party packs, taking only the Fritos and putting them back into party packs, can be described as a sequence. It's a single matrix of applying all of these processes written right to left. So the single Frito thief in a single swoop can instead apply this transformation right here. And written out, that's going to look something like this. So if you multiply these together, this represents a single transformation of the Frito thief stealing exactly only the Fritos from the party packs. This form of a matrix right here is what's called a similar matrix. So the main idea of a similar matrix is it's going to perform the same operation under a different basis. So in this case, these two matrices right here are similar because they're going to perform the same operation under different bases. One of them is the Frito thief under party packs, and one of them performs the operation of stealing the Fritos from the number of bags. All right, so let's go into what a similar matrix is. All right, so A is similar to B if there is an S with A equals S, B, S inverse. So above, we were able to write these two matrices because there's an S. And in this case, this S here is explicitly this matrix right here. That's the S. Now you may notice here I actually wrote it slightly backwards. I wrote S inverse. Most of the time you're going to use this in this form. But let's go through some fun facts about similar matrices. So if A is similar to B, these are fun facts. Then B is similar to A. All right, so this sounds technical and unnecessary, but keep in mind the relationship as written only goes one way. So the idea is if we have A equals S, B, S inverse, then we can solve for B by multiplying both sides by S inverse on the left and S on the right. So we're going to multiply A equals S inverse S, B S inverse S. And now those S inverses on the right are going to cancel. So if you have if A is similar to B, then you get a relationship that says B is equal to S inverse AS. And just keep in mind, that's the same thing as S inverse A S inverse inverse. So the inverse of S is itself. And so now the matrix the matrix you want to do the similarity is S inverse. So the definition says two matrices are similar if there is a matrix that you can put it in this form. And so from going from A to B, the similarity, the matrix you need in one is S, and going backwards is S inverse. And that means that they're going to be, if one's similar to A, if one is similar to the other, you also get the reverse direction. All right. Another thing that may seem very straightforward, but A is always similar to itself. Right. And we can do that because we choose S if there is an S. So we can just choose the identity. We choose S to be the identity. The inverse of the identity is the identity, and the identity times anything is A. So A is, that's going to hold. So we just choose S to be the identity. And the other thing is if A is similar to B, and B is similar to C, then A is similar to C. So the main idea of what's happening here altogether is it says a similar matrix is the same operation under a different basis. And the similarity, this S that we're talking about, this S right here is just what is the change of basis that we need to make it really do the same thing. Right. And the proof of this fact, if we know that A is similar to B, and we know that B is similar to C, here the S's don't have to be the same. So I'm going to use T instead. We can write A as ST CT inverse S inverse. So here we're just substituting. So we're substituting for B. And now we're going to do a couple of matrix manipulations. So we're just going to get rid of those parentheses. And then also remember that for inverses, we can kind of factor in the inverse if we swap the order. So this is STC times ST inverse. So now the matrix on both sides, instead of S or T, is S times T. And this shows that it's a similar transformation. As long as you have the same matrix on both sides, but one of them is the inverse, and one of them is the actual matrix, you have similar transformation.